Our topic today is intermolecular forces of attraction, often referred to as IMF, intermolecular forces. You could think about two vocabulary words, intramurals and intermurals. If you're thinking about intramurals, that's where the sophomore boys basketball team could play the junior boys basketball team, both teams coming from Westminster. It's within our school. So we have intramurals. Intermurals, however, would be between two different schools. Westminster's girls could play Lovett's girls in basketball. So what we're dealing with today is intermolecular forces of attraction. These are not bonds. We've talked about ionic and covalent bonds. They're not bonds like those. These are much weaker forces of attraction. Sometimes I think of them as being maybe no more than 2 to 4% as strong as the bonds we have discussed previously in class. So there are three main types of intermolecular forces of attraction. And the first, named after a man, is often just called London forces. Other textbooks may term it as dispersion interactions to differentiate it from bonds. So I'll usually use all three words, London, dispersion, interactions. These are the weakest of the three forces that we'll be discussing. And what you need to understand is that these forces are present in all molecules. All molecules have this force. The difference is not all molecules have this force to the same extent. So the smaller the molecules, the smaller the London force. And the larger the molecule, the larger the force. So larger molecules have a greater London force Now, to get into this thought, I want you to consider what would be the smallest molecules that you could think of. What would have the weakest London forces? And usually, I would think of gases. Looking at the periodic table, I would think of things like hydrogen and helium. Hydrogen and helium have the weakest London forces, holding them together. And if you were to talk about which one of the two, I guess I could try to do a kind of a diagram, but remember that hydrogen atoms are actually diatoms. And so what we have is an overlapping of these energy levels in our hydrogen molecules, which makes hydrogen larger than the helium atom because helium exists as a single atom. So the molecule with the weakest London force is going to be helium, and hydrogen is very close behind it. Now, the larger the particles, the larger the force. If I had to try to describe this force, it's often talked of in terms of ease of polarizability. Ease of polarizability. And so if you look at this picture here, we know that there are two electrons that is present in a helium atom. And the question is, how easily distorted would this electron cloud be? If these electrons are moving randomly around the nucleus, we would expect these like charges to repel one another and be relatively far apart, so that the molecule as a whole would be net neutral. But in their random travels around the nucleus, it would be possible for a brief moment in time for one electron to be found closer to another electron. This is going to set up a polar molecule, an instantaneous dipole. For one brief second, both of these electrons would be on one side of the atom, making one side of the helium atom slightly more negative, if this were to move to this side, and the other side slightly more positive. So we're setting up a brief instant polarity. Now, as soon as these two electrons find that they're too near one another, you know they're going to repel. So, small molecules like this can have an instantaneous dipole. Size, then, is going to be a factor in the strength of the London force. The larger the molecule, the more easily it is going to be polarized. So, like, take iodine with its many different energy levels of electrons. Those energy levels of electrons, those electrons further to the outside, can be more easily distorted. They're not held as tightly by the nucleus. Small particles have small London forces. Large particles have larger London forces. The other thing that you might consider here would be something like a chain. Let's look at a chain of carbon atoms. I'm just showing you the backbone here. And here we have butane, 4 carbon atoms in the chain. And you can imagine that this is neutral, that all the electrons are equally distributed around the nucleus of the carbon atoms. But what if for a brief second, here in this carbon atom, the electrons were distorted, so that the electrons were more on one side than the other, setting up a brief polarity, excuse me, where one side is slightly more polar and the other side is slightly more negative, and one side is slightly more positive. Well, the carbon atom next to this is going to respond to this. If there are more electrons on this side of the carbon atom, then this is going to affect the carbon next to it. Like charges repel, so the electrons on the second carbon atom would be shifting more towards the right, setting up a polar molecule here. And this would run down the chain, this shifting of electrons, creating instantaneous dipoles on each of the carbon atoms. So because of that, this dipole moving down the chain is going to last longer than it would in this bigger molecule than it would in the single atom of helium. So when you look at London forces, I like to think that larger depends not only on mass, but on volume. And that's why you need to have some concept of VSEPR shapes. Also, you want to think about the fact that how long or how hard is it to distort the electron cloud around the central atom. Now, the second intermolecular force of attraction is called a dipole-dipole. Dipole-dipole forces are permanent polarities, permanent dipoles. Boy, I hope I spelled that right. Permanent polarity. While here, with London dispersion interactions, I think of this as being instantaneous. Instantaneous dipoles, existing briefly. These are permanent. So, if we're looking at permanent dipoles, well, we should consider ET phone home. Things that have F, O, N, and Cl. those molecules that have these elements off to one side, not equally distributed around a central atom, are going to be polar. You've got to be able to identify polar and nonpolar molecules. So if you have a polar molecule, permanently polar because of fluorine, oxygen, nitrogen, or chlorine, that is asymmetrical in its location in the molecule, then you set up a polarity, something like HCl, where we would show a dipole moment, indicating that the chlorine is permanently the more electronegative end and hydrogen is the more electropositive end. Something like HCl would have a London force. All molecules have a London force. But HCl would have an additional force because it would have a dipole-dipole. Now, what does this mean? Well, if you have something like hydrogen, the only force that it has holding it together from one hydrogen molecule to another is a very weak dipole-dipole interaction. These intermolecular forces are between two different molecules. And so this is going to be a very weak force. That's why we find hydrogen in the form of a gas. HCl, if you had two molecules of HCl, there would be this force of attraction, which I'm drawing in red now. And not only would it have a London force, but it would have a dipole-dipole interaction. This would pull the molecule closer together, having stronger forces of attraction between the two molecules. And so, even though HCl is a gas, it is more easily liquefied, turned into a liquid. So the dipole-dipole forces are permanent dipoles and stronger in most cases than London forces, but not always. And then there's the last type of intermolecular force of attraction. This last force is called, not a great term for it. It's called a hydrogen bond. Now, hydrogen bonds deserve special attention. So I'll just finish this video by saying that hydrogen bonding can only occur when you have a highly electronegative element So if we're talking about high electronegativity, FON, but we are not going to see chlorine capable of hydrogen bonding. A highly electronegative element is attracted, not bonded, attracted to the hydrogen of a second molecule. We'll get this definition down, and in our next video, we'll look to see how hydrogen bonding becomes so important. In molecules like water, remember that it's bent and it has two electron pairs. Not only would we show our covalent bonds, but there could be the hydrogen bonds where another water molecule, this oxygen, is going to be attracted to the hydrogen of a second water molecule. So I guess what I could finish up with was by saying that if I have water, not a great drawing here, and another water molecule, that between two water molecules I would have London forces. I would have dipole-dipoles. And I would have hydrogen bonding. Compare this. Hydrogen only has London forces between it, so it's very far, the molecules are very far apart and hard to liquefy. HCl has London forces and dipole-dipole, a little easier to liquefy. But water is held together by by London forces, dipole-dipole, and hydrogen bonding. Water exists as a liquid. We'll continue in our next video.